everyone, my name is Sandeep and today I would like to talk about the paper Smoothed Analysis of the Condition Number under Low Rank Perturbations. This is joint work with Rikhav. So before I begin the talk, I would like to highlight the driving question behind this work, which is how does the condition number behave under low rank perturbations? Now let me start the talk by giving some motivation. So first, let's define the condition number. The condition number of a n by n matrix n is simply the ratio of the largest to smallest singular value. Now, why is this quantity useful or important? It turns out that in many algorithms, this quantity has a huge impact on the runtime and performance. And in general, we want matrices whose condition number is bounded by some polynomial in the size of the matrix. And we say a matrix is bad otherwise. And of course, we really don't want bad matrices. However, it turns out that in practice, most matrices we encounter actually have very nice condition number. So to explain this, the smoothed analysis framework says that, okay, this is potentially true because in the real world, many matrices arise from some scientific or observational process which results in us actually observing an underlying matrix plus some noise. So to sort of mathematically explain why this might help, there is a classical theorem by Shankar, Spielman, and Tang that says if we take any arbitrary matrix M and add a dense Gaussian matrix E to it, where every entry of E is from, let's say, the standard Gaussian distribution, then the resulting matrix is unlikely to have very smallest singular value. Note that I'm going to be ignoring the largest singular value from now on because it turns out that bounding the largest singular value is really easy. For example, if you have bounded entries. So the challenge in analyzing the condition number actually just comes from analyzing the smallest singular value. So anyway, towards sort of the heuristic explanation that I outlined previously, their theorem says, okay, if we start with any matrix M and add a dense noise matrix to it, then it will have a nice condition number with very high probability. And it turns out that this statement that's on the slide is actually true not just for Gaussian noise, but for a whole general class of distributions. So our goal in this paper is, can we get a version of the statement where instead of adding a dense Gaussian noise, can we add a low rank noise? So you might be wondering, why do we care about low rank perturbations? Well, if we actually wanted to sort of initialize this theorem, we'd have to generate a dense matrix, which would, for example, be very time and space consuming. So if we had, let's say, a low rank perturbation, in particular, let's say a rank k perturbation, then we would only need space nk rather than space n square to sort of initialize and store this random matrix E. And it turns out that low rank noise is actually natural in many applications. For example, in many matrices in data science actually have low rank structure. And of course, if we use a low rank perturbation, then we can use less randomness to generate the low rank perturbation than the full dense random matrix. So these reasons and more sort of motivate studying the previous problem under a low rank perturbation. So let me briefly talk about our results. Our first result is the following. Let's say we have an n by n matrix M of rank n minus k. And let U and V be n by k Gaussian matrices. Then if we add uv transpose to m, then m plus uv transpose is unlikely to have a smallest singular value. Note that on the right-hand side, we have a dependence on the n minus kth singular value of m, and this is sort of unavoidable because we're adding a rank k matrix to a rank n minus k matrix. Our other results include generalizing the above theorem to a complex Gaussian noise, and we also have a result that gets rid of the rank n minus k assumption of the input matrix M. And it turns out that the probability dependence that we're getting is sort of the right kind of dependence. In particular, if we go back to this theorem, what we're seeing is that the probability that the smallest singular value is less than some polynomial is bounded by another polynomial. And that's exactly the type of dependence that we're getting also. And we also have some results on discussing how low-rank noise models could apply to other problems in the smoothed analysis framework. So let me briefly sort of outline why extending the condition number result to low-rank perturbations is hard. And the main reason turns out to be that if we add a low-rank perturbation as before, as shown here, randomness is sort of shared across all rows. And to see that, suppose we're adding a rank 1 random matrix, right, which is shown on the right-hand side. We have a column vector times the row vector. And turns out in this case, the randomness of the row vector will sort of appear in every row of the resulting matrix. And this is very hard to analyze because randomness is sort of shared across all the entries. And this actually makes all the previous proof strategies used for the dense case pretty useless. And to see why that is, let me briefly outline what the previous proof strategies are, which is the following. In the dense case, it turns out that to analyze the smallest singular value, it's enough to understand the distance between, let's say, the first row and the span of all the other rows. And why is that? So, for example, imagine that your matrix has singular value 0, which means it's singular, so some row must be in the span of the other rows. So in particular, it turns out that if we understand this distance, then we can sort of analyze the smallest singular value. So on the right-hand side, there's a diagram where the blue plane sort of represents the span of, let's say, the last n minus 1 rows. The blue dot is the first row, and the red vector is the normal vector of the span. So it turns out that in the dense case, all we need to understand is the dot product between a random vector, which is the blue dot, dotted with an independent vector. And it turns out that there are many tools to understand such things, which we cannot use in our case. So let me offer like a high-level overview of the proof of our first theorem, and it's stated here. So the idea turns out to be that we want to decompose our input matrix M into blocks. In particular, let's talk about a lemma that's very useful, which is the following. Suppose our matrix, and here M is in any arbitrary matrix, not necessarily an input to this theorem. Let's say that our matrix is represented in this block form. Then it turns out that we can bound the smallest singular value of this matrix in terms of the operator norms of each of these block components. And the most important thing turns out to be this m over a factor, which is called the square complement of a. So the first step in our proof of theorem 1 is to sort of write our matrix in block form and use the decomposition that I talked about before, and then bound the operator norm of each piece separately, which will allow us to bound the operator norm of M inverse, which is the same thing as bounding the smallest singular value of M. Okay, so now let me give more details. Our goal is to understand the smallest singular value of an input matrix M plus UV transpose, where U and V are n minus k, n by k Gaussian matrices. So first, it turns out we can assume that M is the diagonal matrix due to the rotational symmetry of U and V. And then we can write M plus UV in this block form, where we're just sort of separating the k by k blocks with the n minus k by n minus k blocks. And then the next step is to use the previous lemma that I outlined. And the hardest part of that is to analyze the square complement, which is shown in the screen. It's a really messy statement or messy expression, but it turns out that magically an inner term is 0, which simplifies our analysis a lot. In particular, the term on the screen turns out to be equal to 0, and this entire messy term is just can be very easily understood. So let's go back to the lemma. We have this lemma from before, and we have our decomposition down below. And we will want to sort of match the pieces by pieces in the lemma with the decomposition that we have. So in summary, the proof of theorem 1 sort of follows as follows. We write our matrix in block form, we analyze the square complement, and turns out the leftover terms actually only depend on U and V, which we know how to bound because they're Gaussian matrices, and also the n minus k singular value of M. Now let me briefly discuss the proof idea of the general case, the general rank n case, where we don't assume that the input matrix has rank n minus k. It turns out that the previous idea I outlined only sort of works when the input matrix has rank n minus k, and that's because this square complement works out to be a very nice expression, and that's not going to be true in general. So what we actually do is we carefully adapt the ideas from the dense case that I talked about before, but it turns out to be very tricky and uses some very tricky conditioning. So a natural question to ask is, do our results extend to other distributions besides Gaussians? And this is natural because it turns out that in the dense case, one can replace Gaussian matrices with a whole variety of distributions, such as sub-Gaussian distributions. So we actually show in our paper that in general, sub-Gaussian perturbations in the low-rank noise model cannot work, and we have an example that shows that. And in particular, our example is with plus and minus 1 random variables, which are sort of the most natural sub-Gaussian distributions besides actual Gaussians. And it turns out that if we add a rank 1 perturbation to a rank n minus 1 matrix, where the perturbation is coming from these plus and minus 1 random variables, then the resulting matrix will actually be singular with constant probability, which is very different than the dense case. So now let me briefly highlight some numerical experiments. In this plot, we're taking a family of very ill-conditioned matrices. And the blue line is plotting the smallest singular values of these family of matrices as the size grows. And then the orange and green lines are showing what happens to the smallest singular value after we add a dense and a rank 1 perturbation. As you can see, like in the original case, the singular values are decaying sort of exponentially, but after we add either a dense or a rank 1 perturbation, they become much nicer. And on the right-hand side, I'm plotting the time taken to perform a matrix vector the operation. If we add a low rank noise, then this the operation is very fast. In particular, it's sort of linear time versus taking a quadratic time if we add a dense random matrix. So the natural question is, can we apply the low rank noise model to other problems that have been sort of very carefully analyzed in the smoothed analysis framework? And these include problems like the simplex method, k-means clustering, and so on. And the message for this part is that we actually need new ideas to extend previous analysis to the low rank noise case. And in particular, let me highlight one such problem where we encounter such problems. So let's consider the case of k-means clustering. Now, the goal of k-means clustering in the smoothed analysis model is to show that this algorithm called the k-means set algorithm converges in polynomial time. So in the smoothed analysis framework, it turns out that we can show that if we add dense Gaussian noise to the input, the algorithm actually converges in polynomial time. So it turns out that the key lemma that goes into the proof of the dense case is the following. Let x be a Gaussian vector where each entry is an independent standard Gaussian, and let b be the ball of radius epsilon around the origin. Then a key lemma that is used in the proof of the smoothed analysis result is the following, which says the probability that x lies in the ball is at most some exponential factor in epsilon. In particular, is at most epsilon to the d, let's say. Now let's translate this lemma in the low rank case. In the low rank setting, instead of having dense Gaussians, we have let's say low rank perturbation, which is these outer products of vectors. It turns out the natural statement that we want to prove in the low rank case is what is the probability that y times x is in this ball, where x is a d-dimensional Gaussian vector and y is another independent random Gaussian. And it turns out that the probability actually increases significantly from exponentially small to only polynomial in epsilon. And in particular, the bound that we get is the probability that y times x is in the ball is only epsilon over root d instead of epsilon to the d. And it turns out that because this bound degrades so badly, we don't have enough probability to union bound over exponentially many events, which is done in the original proof in the dense setting. We prove this low rank version of this interesting statement. And the proof is actually really simple. It turns out that heuristically this vector x will have, let's say, norm like square root of d, and since y is independent of x, y times x will roughly be distributed as Gaussian variance d. So we can sort of chain these statements together to get the bound. It would also be interesting to generalize the low rank noise model to other problems that have been studied in smooth analysis. And also, are there other new noise models in smoothed analysis that also make sense?